This is Mrs. O'Neill for AP Chemistry, Chapter 16, Section 4, the pH scale, something I'm sure you've heard before. In this case, you're going to understand that that pH scale describes how acidic or basic an aqueous solution is. And you probably already know that a pH of 7 means that it's neutral, a pH below 7 means that it's acidic, and pH above 7 is basic. So to test the diagnosis of diabetic coma, a doctor orders several tests, including the acidity of the patient's blood. Results from the test will be expressed in units of pH. You will learn how the pH scale is used to indicate the acidity of a solution and why the pH scale is used. So at this point, pause the video, fill in any blanks, and then play to hear my words. So this is the simple pH scale that you're used to. Right in the middle is neutral. Anything to the left of that, 0 to, let's say, 6.99999 is acidic, and 7.00001 to 14 is basic. So it's nice because it's in alphabetical order, right? Acid to base, A to B, and of course your neutral's right in the middle. So these are the pH of everyday things. I just like to kind of bring these to your attention, as well as let's look at this pattern. Again, chemists don't like to use the pH scale of 0 to 14 very often. They like to dig in deeper on the molecular level and go, well, if we have a pH of 2, like lemon juice, that means that our H plus, or the hydronium concentration, is 1 times 10 to the negative 2. Pure water would be negative 7, and let's say something like Drano is times 10 to the negative 13. So hopefully you see some kind of pattern, and this all deals with logarithms. And we're going to do a Poggle, if we did not do it already, about logarithms and how they work. So there's also what's called the pOH scale, okay, which should make sense to you. If the pH scale is the negative log of the H plus concentration, well, the pOH scale is going to be the negative log of the OH minus concentration. So if we add those two together, we get 14, and we get that Kw value, right? That 1 times 10 to the negative 14. So we want to remember, and sometimes this is hard to remember, as we increase the H plus concentration, our pH will decrease. So we want to remember that that pH scale goes from acid to neutral to basic. So the lower the pH number, the higher that H plus concentration is. So again, this is just a nice visual, getting you to understand that we have acidic solutions, we have neutral solutions, and we have basic solutions. But it's going to be based off of the H plus concentration, pH, and pOH is going to be based off of the OH negative concentration. But I also want to remind you that anytime you are asked about a solution being acidic or basic, almost always they are going to ask for the pH value or the H plus concentration. They're not too worried about how basic it is. They're worried about how acidic it is. So again, hopefully you see that relationship among the H pluses concentration and the OH minus concentrations and what they are as far as that simple pH scale. And again, I like to give you some idea of certain things that you've dealt with in everyday life if it's acidic or basic. So hopefully this makes sense. Everything equals 14. So if we have an H plus concentration of negative 2, we're going to have an OH concentration of negative 12 because adding them up equals negative 14. So pause the video, read, look at this diagram, and see if you can answer the question. Hopefully that makes sense, right? As you're increasing the pH, you're decreasing that H plus concentration. But again, most questions are going to ask you either the pH or the H plus concentration, even though they might give you something that's basic. Again, pause the video. It's really important to understand and read these graphs. Hopefully you got those answers. So here's example 1. So if we have an H plus concentration of 1.0 times 10 to the negative 3, we want to know what the pH value is. Well, pH is the negative log of H plus. We're going to plug and chug our numbers, take that negative log in your calculator, and you get an answer of 3.0. And again, that would be sig figs. And we'll talk a little bit more in detail about that when we do our Poggle. Here's example 2. Now I'm giving you the pH. I want to know the H plus concentration, so we're going the other way. So hopefully something comes to mind called an anti-log, right? So if we usually take the log of something and we want the opposite, we have to take that anti-log of something. So here's our pH equals negative log over H plus concentration. We're going to plug in the 3.76. Now we need to take that anti-log, and in your calculator you can either do second log if that's your specific calculator, or you're going to do 10 to the negative 3.76. You should have like a 10 to the X button as well. So try either one of those, pause the video, and see if you get this answer. Hopefully you got 1.74 times 10 to the negative 4, and because it's asking for concentration, we need the unit of molarity. pH does not have a unit, but molarity does, so we want to remember that. Here's an example 3. This is what I meant before. They're giving you the OH, the hydroxide concentration, but they still want pH. Well, that's when we use the POH first. So we're going to use the POH, we're going to plug and chug, we're going to get 6.59 as our POH, but again, it's asking for pH. So we have to do that extra step. We have to say, well, we know that the pH plus the POH equals 14, so we're going to take 14 minus that POH value to get an answer of 7.41, 2 decimal places for our sig figs for the pH value. So a lot of times that's what they do. They're going to ask for your pH even though they're giving you an OH minus concentration. So example 4, I will go through these little by little, but there's A, B, C, D. A, you should be okay with, but remember it's strong. B, you should be okay with, but there's 2 hydroxide ions, so just take that into consideration. And C and D deals with percent dissociation. So we'll talk a little bit about that as we go through these examples. So here's example 4A. See if you can do it yourself, but if you can't, that's okay. We're going to go through it. We need that balanced equation. All the coefficients are 1, makes it nice and easy. Because it is strong, the 0.01 equals the H plus concentration because it's not at equilibrium. So we have pH equals the negative log of 0.01, which is a negative 2. We take that negative of that, and we need to, again, pay attention to those coefficients, and there's no unit. How about 4B? Now again, as I said before, we're going to look at that strong base turning into calcium plus 2 ions and 2 OH minus ions. So if we have the 0.05 to start with, we're actually going to have 0.1 OH minus concentration. So we need to remember we multiplied that by 2. And again, we need to find POH before we find the pH, right? Because this is OH concentration. So 0.05 times 2, because of the balanced equation, we have a POH value of 1, and then we can take 14 minus 1 to get 13 as our pH value. So again, at this point, you might even want to pause or replay this part to make sure you're understanding that first of all, it's a strong base. Second of all, we have to pay attention to those coefficients. So what we start with in molarity, we're doubling for our OH. Plus, because it's OH, we need to find our POH value, in this case 1, before we find our pH value, what they're really asking for. 4C, now what the heck does this percent dissociation mean? Well, HF is a weak acid, so here's our reaction again. HF is in equilibrium with H plus and F minus. So what's happening is that 10% is telling me that 3 times 0.1, there's our 10% association, that's how much H plus ions we really have in there. So let's look at that ice box, right? So from that equilibrium chapter, just to get you thinking where all these numbers are coming from, this is how much we start initially. But if only 10% dissociated, that means at equilibrium, we end up with a 0.30 molarity for our H plus concentration. That's where that 10% is coming from. So now we can actually just take our pH of the 0.3 or negative log of that H plus concentration, which is 0.3, and we get a value of 0.52. So why don't you give it a try? Hopefully now that you're understanding, again, I'm giving you a dissociation value. So think of the reaction, think of that ice box, think about the fact that this is, it has OH in it, so it's probably a base, which means you have to deal with the POH first before the OH. So this kind of has a little bit of everything except for, I believe all the coefficients will be 1, so that's helpful. So pause the video and see if you can figure out the answer. Did you get that for your reaction? Did you get that for the dissociation? Think about your ice box. You started with 2.5. It dissociated 5%, so you're left with a 0.125 OH concentration. Find the POH first, which is going to be your negative log of the OH concentration, or the negative log of 0.125. But now remember, we're going to subtract that from 14 to actually find the pH value that they're always looking for. And does this make sense? Our NH4OH is a base, so our pH value should be in the basic scale. So again, take a look at this. Make sure you're understanding all those values, where they're coming from, and the why. And again, the lower the pH, the higher the H+ concentration. And again, we just measure a pH using a pH meter. It's just another tool or a device that scientists use to measure pH. See you in class.